5, but so it's Wednesday afternoon, and after all this turmoil with my bad announcements and time errors and all that, we're still here at 16 Central European Time. The summertime ended last weekend, was it? Or maybe the weekend before that. I don't even remember. So today's seminar will be presented by, I don't know which order, but Aisha Kermishe and Yanxi Fu from UCLA. And they will talk about a review of CISS at the limits towards quantum spintronics, if I got it right. I hope so. And I don't think I have to say more. We know how to behave with questions and all that. So I'll leave the stage to the two of you. Please share the screen and you can go.
All right. Thank you, Prof. Franson. Hold on a second. Let me just see if this. Right then, do you see my screen?
Yes.
Yes. Thank you. Thank you. Hold on. Let me just enter the slideshow mode. Slide share mode, whatever it's called.
Yeah, okay, that's good.
Okay, all right then. So just to begin, thank you everybody. I appreciate that everyone has taken the time out of your busy schedules to hear what we have to say. So quite simply, we at the Quantum Biotech Lab, Biology Tech Lab in UCLA, have been primarily interested in the possibility of using biomolecules in qubit manipulation, with CISS as our primary mechanism. So basically, the structure of this talk is going to be something that's fit for a more general audience, a more interdisciplinary audience, that sets out to give a very brief perspective of what CISS could offer from the lens of quantum spintronics and what further work might be needed to cast a broad net to the sprawling density of CISS that might get us there. So, yes. Having said that, this leads us to nicely split our talk into two halves. The former of which we probe the possibility of using CISS in biomolecular spin qubit operation, and the latter of which we take a rather big picture view of not what we know about CISS, but what we don't know about CISS, and to reflect on how intricately connected it is to so many different fields across the disciplines. So without further ado, let us spend some time trotting some well-trodden ground and start with a recap of the most basic picture of CISS. So when we inject an electron current through a helical biomolecule, the current will become spin polarized. One spin state will be preferentially transported along the helix, while the other will be preferentially transported in the opposite direction. Exactly which state each will be is dependent on whether the molecule has a left or right-handed helical structure. Now, this neatly encapsulates what most of us think of chirality-induced spin selectivity. And how might this observed phenomena proceed? So if we consider the world from the electron's rest frame, quite similar to how a moving electron produces a magnetic field in laboratory frame, yet it still only sees a radiative electric field coming from its own perspective, which is the essence of the Biot-Savart law. We have here an electron moving through a laboratory frame that holds ideally no magnetic field. But from the electron's perspective, it sees a world where charge distributions being biased along the molecule are rotating around it. So we say that it experiences an effective magnetic field. An effective field which couples to the magnetic moment of the electron and creates a spin orbit field, where the spin and the momentum of the electron are locked together. They help describe each other, and we see this in the very elegant energy dispersion diagrams here, which depicts the spin momentum kind of energetic preference going on. The trouble is that to effect the large spin polarization strengths we observe in experiments, such a naive analysis gives us an expected energy gap of about hundreds of milli-electron volts, which is about 2 orders of magnitude away from what we'd expect when we are just taking the usual spin orbit field strength of your regular hydrocarbons. And this, of course, is one of the big questions behind the CISS mechanism. How do we account for this anomalous energy gap? And without knowing what it is or where it comes from, trying to imagine some sort of fine control over it becomes a bit of a case of quick sticky fingers. So to gain a bit more insight, let us delve into a microscopic picture of CISS. So suppose I inject an electron wave packet into the molecule and have it travel along the molecular axis. Its spin state, I define, is such that it is quite simply going the wrong way. So very intuitively, we think that something must happen to put it back on the right path. Unfortunately, this task cannot be performed by magnetic fields alone because all they do is precess the electron spin along its axis. What is needed for the observation of spin polarization, rather, is scattering events. And this brings to mind, of course, some sort of lossy energy transfer in interaction with the environment on the electron's part. So in Spintronics, we can broadly classify these processes into two commingling pictures. Pictures normally used to describe spin depolarization, but which nevertheless are applicable for our purposes. The first is the Elliott-Yafet picture, where spin-orbit coupling, as the name describes, produces wave functions that are admixtures of spin and orbital states. So our spin and orbital angular momentums no longer provide us good quantum numbers, so we fall back to a wave function basis built on the total angular momentum instead. So in practice, what this means is that our spin-orbit coupling causes spin-up and spin-down states to mix together. Now, this mixing is usually negligibly small, unless the spin states form some sort of nearly degenerate bands. In such a case, when any scattering event occurs, it possibly enacts a kind of projective measurement onto our electron that can cause spin decoherence, such that we might observe that perhaps the spin has flipped. And this forms the backbone of what we might imagine to be a spin flip procedure. On the other hand, we have the Diakonov-Perel picture, the gist of which is basically that the effective magnetic field the electron feels is not uniform throughout our medium. When our electron gets scattered, its momentum changes. As it does so, the effective magnetic field axis it is precessing around tilts, and it is now made to precess along that new axis. What happens eventually after a long travel length and time is that our electrons goes through so many scattering events. This essentially constitutes a guided random walk across our medium, such that we lose all information of whatever state the electron might have initially been prepared in. This describes quite generally spin dephasing, but it also constitutes the spin filter picture, which relies on the electron's momentum change and not its spin flipping. Since we have established that spin polarization necessitates some sort of spin relaxation process, one might consider CISS in quantum control to be a lost cause a priori. But we now pose a rather subtle question. Do these processes primarily occur in the molecule itself, or does the molecule prepare some sort of superposition that is then projectively measured by the detector, by the leads, or whatever gives us our classical charge current readings? And this segues very nicely into our application of interest. Can CISS be used to design spin qubit devices? Two immediate questions that come to mind are, does CISS preserve electron spin coherence during transport? And if it does, can it be used as a tunable spin rotator? So the first question can be simply considered in terms of scattering events. Is the electron in the diffusive transport regime, where it meets many scatterers along its path, or is it in the ballistic transport regime, where it meets no scatterers at all, either because there are no lattice disturbances in the space around it, or perhaps the length of travel is simply that short, such that we do not have to consider such scattering events. So here, some of us might be thinking, as the picture depicts, in a more semi-classical sense, where your electron is particulate, where your lattice is particulate, and scattering essentially means that they are bumping into each other of sorts. The electron is bumping into impurities, etc. Now, we would like to clarify that we use scattering in a more general sense, where any event that perturbs our electron wave packet constitutes a scattering event. For example, all of your perhaps traditionally non-local interactions from electromagnetic fields et al., we can portray to be local as well by means of some virtual particle or gauge boson exchange. Now, if the electron does scatter, do these scattering events result in dephasing? This seems like quite a silly question at first, but it is not a very trivial thing to consider, actually. Recent advances in spintronics have resulted in the generation of persistent spin helices. In short, by engineering our spin-orbit coupling field in such a fine way that spin is unaffected by relatively small shifts in momentum, we can provide some sort of protection against spin relaxation. So on the right, you have a nice Fermi branch diagram depicting all the possible momentum values an electron situated in the highest occupied molecular orbital can take. And as the arrows depict, we see how for a suitable spin-orbit coupling field, the effective magnetic field an electron experiences at any given momentum it is traveling in remains rather stable given this configuration. So with this in view, we can see an emergence of quantum control in spintronics in general, which is a traditionally semi-classical field. And now still, we can push the envelope slightly further. If CISS can be used to design some sort of tunable spin-orbit rotator, might CISS perform as such in a hot, wet, and messy biological context? And if the answer is negative, what insights can we nevertheless draw and apply towards some sort of quantum computing or quantum control context? So before we carry on, let us try to extend this idea connecting CISS, semi-classical spintronics, and quantum control. So we now draw an intuitive and non-rigorous, of course, connection between spin relaxation in semiconductor spintronics and spin decoherence in quantum computing. Now, suppose I prepare some sort of initial spin-up electron population. Classically, we take the vector of the spin's expectation value, and this vector precesses at some well-defined rate around the magnetic field axis. After scattering, enough spin flips might occur such that our electron population is thermalized, and we receive some 50-50 distribution of readouts, if that happens to be what the Boltzmann average gives us. And we can characterize this by the thermal relaxation time, T1. Furthermore, we can expect that as our electron goes through its guided random walk, our precession rate against the initial field axis gets so perturbed that we also lose all information of that within our ensemble. This is characterized as a transversal T-phasing time, or T2. So how might we transplant this to a quantum picture? It's not, and it's not as far-fetched as it might seem. So suppose we prepare a single electron wave packet in some sort of superposition that we can now describe in the Bloch sphere. Our precession around some magnetic field axis amounts to an applied rotation operator on our state vector. And now picturing scattering events as a series of rotation operators undergoing perhaps some sort within some sort of lossy evolution, we can similarly define a thermal relaxation time and a T2, which we can now understand as not only as ensemble dephasing time, but also a loss of superposition. So we do not exactly vouch for a one-for-one correspondence here, but we do see a direct overlap between semi-classical and quantum indexes, which hints to us that results obtained for classical measurements in CISS can help inform us of its expected behavior in quantum control. But what do we expect from CISS per se? We expect noise, we expect room temperature readings in a wet environment, which is a very far cry from the near 0 Kelvin vacuum settings, which we most associate with quantum control. Considering CISS in a biological context means that we have to consider how electrons couple to your phonon bath in an inherently open quantum system. Now, this alone provokes intense suspicion that electron transport in CISS ought to be incoherent. But let us take a more fine look at what constitutes electron-phonon coupling. So first, we have our usual conception of how phonons interact with electrons. An electron polarizes the lattice it is in, and mutual interactions between them result in some sort of deformation potential coupling. Now, because of this, the lattice strain is essentially inhomogeneous and gives rise to fluctuating electric fields within the lattice. This tends to spatially localize states, and electron transport across the lattice is now best described as a disorderly hopping mechanism. On the other hand, in polar materials like gallium arsenide, phonons can give rise to electric quadrupole moments, creating a homogeneous strain field that helps to establish relatively long-range electric fields, favoring spatial delocalization of your eigenstates. With these short and long-range electrostatic forces that thermal motion effects, one can now picture two possible mechanisms. CISS might be best described as a temperature-enhanced spin-incoherent hopping across localized sites, or it might involve some sort of noise-assisted band transport. And the ultimate question that we have to ask here is, does vibronic coupling delocalize sites more than disorder localizes them? Of course, the latter option sounds far more far-fetched than the former, but we think it would be quite premature to write it off just yet. So if we look to the right of the slide, what we find is some iridium gallium arsenide channels being etched out of a wire to sub-micron width. Electron transport through these quasi 1D channels essentially is shown to have a much higher dephasing time than electron transport through the usual wires, which we can consider very simply to be the Diakonov parallel mechanism being highly suppressed simply due to the removal of your momentum degrees of freedom. And on the right, we see how electron-phonon coupling can give rise to large polarons formed under long-range electron-phonon interactions, which moves coherently akin to a free charge carrier with large effective mass within the lattice. Unfortunately, the mobility of such large polarons diminishes with temperature, so additional protection from decoherence might have to be invoked if one is to realistically consider coherent large polaron transport across a cis molecule. Nevertheless, I hope it is relatively evident that there are certainly avenues for the suppression of spin decoherence mechanisms, and that electron transport characteristics of not just semiconductors, but also organic semiconductors in general, provides very rich and non-trivial grounds for further study. So by this point, I think we have sufficiently covered the question of whether CISS might be usable for quantum spintronics applications. And we now move on to the latter half, which is a quick survey of the current state of CISS to see what more needs to be done before we can find some sort of well-grounded answer to the question of fine control of CISS and its application to spin qubits. So I think coming into CISS, one tends to have the view that CISS is a chiral molecules phenomenon with electron transport as its main theme. So here we have a bit of a ramshackle diagram where we briefly chart out how CISS has been and might be explored. So of course, on the top left, we have CISS in a quantum spintronics context. Then on a more semi-classical level, we have the bulk of spin valve experiments, where your CISS molecules are adsorbed, hopefully lengthwise, onto some substrate. You then run a current through it and you record, given different magnetization directions of your leads or your detectors. The asymmetry between these current readings gives you some sort of spin polarization index. Then we have our circular dichroism experiments. Essentially, when we fire circular polarized light at some chiral material, we see that there is a differential absorption between left and right circularly polarized fields, a difference that can be simply explained as arising from the light's electromagnetic field, either driving in phase or out of phase electron oscillations within the chiral material. Now, moving away from what has already been very well established in experiments, we introduce applications and extensions of CISS into quantum chemistry and quantum biology. One of the most pertinent of these being intersystem crossing. Simply put, photoexcitation promotes a singlet to its excited state, which can interconvert with its triplet states. And this can form some sort of superposition of singlet triplet states under the influence of spin-orbit coupling. We may expect this to be informative in elucidating the radical pair mechanism, which aims to explain how birds navigate the Earth's magnetic fields. Further still, we may now swap the role of cause and effect and probe possible spin-induced chirality selectivity mechanisms, an endeavor of great relevance to asymmetric autocatalytic reactions like the SOI reaction, where you where you have the alkylation of a pyrimidine carbaldehyde, and this surprisingly results in not some sort of 50-50 race-split mixture containing products of both chiralities, but a strong enantiomeric excess of either chirality. As it turns out, when a product of one chirality is formed, it suppresses the formation of the product of the other chirality. Now, much more is confirmed about the reaction, and perhaps spin physics might be the missing link we need to bridge the gap. And by extension, proposed spin-induced chirality selectivity mechanisms also feature quite greatly in hypotheses about the homochirality of life. Why do amino acids in biological systems, why are they mostly left-handed? And why are sugars, on the other hand, mostly right-handed, when theoretically they could have just been a 50-50 mixture? And perhaps one of the greatest mysteries amongst mysteries lies in chiral transmission and self-assembly. The sergeant and soldier's effect, for example, details how the presence of a small amount of chiral molecules can induce the formation of chiral macromolecular structures made up of other achiral molecules by means of some unknown causative mechanism. So with the sprawling breadth of chiral phenomena in electron transport now laid bare, we see that CISS, as studied thus far, occupies only a small, though very deep section of where it could go. And this is where we would like to make a very subtle distinction. CISS has thus far been explored primarily as a spintronics subfield using chiral non-crystalline structures or soft matter. And this final point is, we think, of key importance because so much of traditional spintronics, of topological insulator research, etc., has been designed for crystalline structures where characterization gives you very stable electronic properties that we can fix to some sort of unit cell in some sort of Brillouin lattice. And biomolecules are far from an ideal test bed in this when we consider things from this frame of mind. So with this difficulty in mind, we can go on to ask ourselves, what do we know about CISS from experiments? So we can briefly go through some key results. For one, we generally receive the largest spin polarizations at room temperature, which strongly suggests that phonon coupling is a key mechanism in enhancing CISS. What this implies about quantum transport is still up for further investigation. We know that spin polarization exhibits some sort of critical length dependence, where it is increasing together with molecular length. More specifically, as the molecular junction gets longer, current flow drops, but it drops much faster for one tip magnetization direction more than the other, which indicates very strongly to us some sort of spin filtering Dyakonov-Perel picture. We know that spin polarization is correlated with charge polarization. One simple proposed mechanism for this is the spin blockade mechanism. When an electron runs through a molecular junction, it gains a non-transient charge polarization that diminishes the electric field across it, because your positive charges are minutely displaced along the field. This charge polarization is accompanied by a spin polarization within the molecule, resulting in non-uniform spin distributions in space. And this sets up unequal tunneling barriers for electron wave packets of some prepared spin state, perhaps, that we might want to inject across the junction. And this in turn affects current readouts. Additionally, we also know that it is substrate dependent. Conductance asymmetries, as we see, depend not only on the choice of biomolecule, but also the spin orbit coupling of the substrate layer itself. In essence, our readings depend on the initial spin polarization of injections being injected from the substrate layer. Lastly, we also know that CISS does not require any chiral centers to operate. We can take an achiral monomer submerged in a chiral solvent and let chiral self-assembly happen such that we get helical structures from our achiral building blocks. After washing away all the solvent and probing the circular dichroism spectrum, we receive opposite responses typical of CISS. Now, this in itself is not very surprising when we consider the general theory of circular dichroism, but it does serve as a very timely reminder amidst a very interdisciplinary cohort that when we refer to chirality, we are almost always referring to some sort of helical secondary structure according to what we have explored thus far. So with all this on display, we see that there is simultaneously very much and quite little to go by when one wants to characterize electron transport in CISS. So to resolve this deadlock, perhaps the first step to take is to concoct some instructive and interpretable theoretical model, some good Hamiltonian that can describe experimental observations, and that can also be used to make predictions on CISS in general. Of course, one can dream. This is a bit of a pie in the sky to behold, but at the very least, however, we can describe what we'd expect from a serviceable starting theoretical recipe for CISS. Our first task is to address helicity dependence in CISS. We can expect great deviation from a linear chain, for example, when we consider atomic orbital overlap owing to our helical structure. Such corrections are adequately implemented by our MDDFT calculations, and to some lesser extent, Slater-Coster tight binding models. One aspect that has been neglected, however, are the non-inertial effects arising directly from helical motion. It is also necessary to consider how we can, or rather how we cannot, properly incorporate semi-classical effects arising from our spin valve setups into calculation. How we can properly characterize or perhaps add or eliminate contributing interactions between experimental setup and CISS molecule. And finally, we have to contend with temperature dependence. Much work in the literature has been poured by our betters into investigating electron-phonon coupling, and there is of course much room for further work. For example, chiral lattices give rise to chiral phonons. So how does coupling of electrons to chiral phonons affect electron transport? But as temperatures increase and we consider nearly degenerate states, for example, in intersystem crossing, we now also have to contend with how non-adiabatic dynamics affects our understanding of CISS. So in the interest of time, we will give only a short overview of the points in bold. So the issue of non-inertial effects, quite frankly, does not come, at least in my case, from a pure interest in matching CISS theory with experiments per se. One might suspect, for example, that they only pose a small correction to the spin-orbit coupling field, similar at scale similar to how Thomas precession adds relativistic correction to Larmor precession. If true, then such an effect would hardly be expected to address the anomalous energy gap. Nevertheless, this doesn't change the fact that we don't quite yet have a grounded and stable first principles analysis we can rely on. And this makes for difficulties in getting an intuitive grasp of some fundamentals behind this theory. For example, from a very just simply knee-jerk reaction, a current running through a helical solenoid generates a magnetic field in the laboratory frame. Then, by extension, does this also mean that an electron being transported through a helical molecule generates one in the laboratory frame as well? Can we expect that this might give rise to some sort of effective Zeeman splitting field? And there are simply many questions to be had when we try to approach CISS from this very fundamental physics angle. So where do we begin and how do we begin? Let us strip all the way down to the bare bones and start by considering a simple electron moving in free 3D space. The motion of this electron is adequately described by the Dirac equation. Now we need to constrain the motion of the electron to, say, a 1D helical path. And we can appropriately draw out such a path by using the Frenet-Serret machinery, where the rest frame at any point of the helix always has the tangent axis following electron motion along the curve, while the normal axis is always oriented into the helix. So this essentially gives us a kind of curvilinear description of electron motion through the helix. All we have to do now is apply Da Costa's thin layer quantization, where we essentially shrink wrap motion all the way down from free space into the helix by assuming some sort of infinite potential that acts as a waveguide. Having done so, we might feel quite secure in thinking that we can now simply go ahead and plug away. So if we generate the Hamiltonian and take it to the non-relativistic limit, we see very familiar terms popping up. We have our kinetic energy, potential energy, rest energy, our Zeeman fields, spin-orbit coupling fields, etc., and etc. The only problem with this analysis, however, is that the canonical Dirac equation only describes an inertial frame of reference. Clearly, the rotating Frenet-Serret frames are non-inertial with reference to the laboratory. So if we have to be very pedantic about things, what we really have to do is break open our differential geometry toolkit and input corrections into the Dirac equation itself. Here we now turn to the generally covariant form of the Dirac equation, where we have to adapt our gamma matrices and provide some sort of affine spinor correction, which helps us preserve Lorentz invariance for the Dirac fermion. This way we can properly describe helical motion of a free electron. The only problem now, of course, lies in generating the Hamiltonian and finding out exactly what and exactly how much we are really missing from having ignored all these non-inertial effects. Of course, this problem happens to be a particularly grueling one, but that is beyond the scope of this talk. Secondly, we also have to consider how experimental setups can significantly deviate from ideal theoretical simplifications. In tight binding models, one often considers electron transport in a time reversal symmetric regime, where no external magnetic field is exerted along the molecular junction. And in spin valve experiments, such an arrangement is very difficult to imagine. spin polarization as gotten from experiments are effectively a kind of indirect magnetoresistance index, or magnetoconductance index as well. Electrons from the majority spin state subband are biased through the molecule. Then the magnetization of the tip determines what spin state it preferentially accepts. And without effecting this difference, we cannot arrive at any spin polarization measurement within the setup. Isolating molecular contributions alone from this process and bleeding out some sort of smoking gun correspondence between theory and experiment is very challenging and still a work in progress. Additionally, it is not enough to simply consider substrate and molecule separately. The magnetization of the setup can be modified when a spin polarized current flows through by means of some spin transfer torque and spin orbit torque, the combined effect of which can greatly enhance spin polarization. So there is a kind of dynamic effect that we also have to characterize and that we also have to be able to grasp very firmly. So lastly, we turn our attention to chemical physics and consider the rather abstract notion of the Berry's phase and Berry's force. So we begin step by step. Let us consider some state vector. We have it undergo slow quasi-static evolution, so it always remains at whatever instantaneous eigenstate it is in, and we have it come back to its original state. We can describe it as having undergone an adiabatic cyclic evolution. The initial and final states are only separated by some global phase change. We might imagine that this global phase change can be easily gauged away and hold no physical significance whatsoever. But this is not the case. When we pop it open, we find not only a dynamical phase factor, which can be gauged away, but also the Berry's phase, which is gauge invariant. That is to say, the Berry's phase describes some inherent dynamical properties of our system and gives rise to true physical forces. To explain what the Berry's phase is, let us turn to some geometric sketching out. So first we consider figure A. Suppose I begin from a point on the north pole of the sphere, and I equip this point with a tangent vector that is always pointing towards the south pole. We now move this point and this vector around the sphere and bring it back to the north pole as seen. What we see is that the tangent vector has now been rotated by some angle phi, which indicates that there is some sort of geometric or path information that is not captured when we only consider the point we are on the sphere. And this constitutes the basis of the Berry phase. So how does this look in practice? We may picture the Berry's phase, or rather the Berry connection, as a pseudo-magnetic field acting on our state vector, a pseudo-magnetic field not in real space, but in momentum space. So let us consider a Bloch sphere, and we consider a spin qubit in a changing magnetic field. Now, S describes our state vector, and R describes our field vector, around which S precesses. Suppose we now make our R vector rotate very slowly, such that no dephasing occurs to our state vector, such that there is no loss of supercoherence, and we have it rotate one cycle around the z-axis. What happens is that the eigenstates of our system have now acquired a Berry's phase characterized by the angle of R against its own axis of rotation. The presence of a Berry's phase results in the appearance of a pseudomagnetic Berry's force, succinctly described by your electron momentum and your derivative coupling, which captures how two eigenstates affect each other based on the motion of nuclei within our system. We can normally assume that the derivative coupling will be very small because nuclear motion should be very slow compared to electron motion. The timescales should just be too far apart. And because our eigenstates should also be significantly gapped from each other. Furthermore, we notice from the equation that the Berry's phase will vanish if our Hamiltonian is wholly real. One might, from this, conclude that there is little loss in ignoring the Berry's force. Yet, things change quite drastically when we consider temperatures high enough for nuclear motion to have some sort of non-negligible effect on the electron wave function, or when we consider nearly degenerate states that are barely gapped. our derivative coupling now becomes significant under such adiabatic non-adiabatic dynamics. But our original definition of the Berry's phase, as we have just built earlier, was based on some sort of adiabatic cyclic evolution. And because of this, we see that we need to find a new formulation for the Berry force, a non-abelian Berry force. To illustrate why this is necessary, let us consider a situation of intersystem crossing, a mechanism of great relevance in photoexcitation-related CISS, where a singlet state converts to triplet states, each of different spin number. We can describe this with a fully real Hamiltonian. And if we evolve this Hamiltonian over time, we find that after the conversion event occurs, the three triplet states no longer travel the same direction in space. This suggests immediately that the motion of the nuclear wave packet is dependent on its spin number, a dependency that likely arises due to the Berry force. Having a real Hamiltonian should have resulted in a zero Berry force if we consider our analysis beforehand, our analysis prior. So this can only be resolved once a proper non-adiabatic formulation for the Berry's phase, the Berry connection, the Berry force has been found. And until then, we have a very tenuous relationship between chemical physics, spin chemistry, and spintronics. Of course, there is much more to consider in CISS theory compared to what we have briefly covered, but we hope that this has given a short glimpse of some very fascinating and interesting and perhaps slightly not so pressing gaps in CISS theory. Although we have gone through a small and basic perspective into expanding CISS to the realm of quantum control, altogether we have done so rather, and having described all the questions that we've had in our former part, we have only been met with more questions in the latter half. So it is only fitting that we end off with even more questions, now forward-looking ones. How much does CISS owe to temperature and how much does it owe to geometry? How do we bridge mechanisms between charge injection and photoexcitation-induced transport in CISS? And how can we design experiments to investigate quantum transport in CISS, something that's being actively pursued in our lab? Can we characterize CISS as a topological soft matter phenomenon? Now, this might sound like a very big contradiction because topological insulators, by their definition, is defined on some sort of symmetry, either in momentum space or in real space. And we have soft matter, which is characterized not by symmetry, but by the lack thereof. So, and last but not least, how do we extend physical insights from what we currently know about CISS towards electron transport in chiral molecules in general? So with that, I end off, and I hope this has given everyone a quick, if slightly touch and go introduction to some of the more deeply embedded issues in CISS. And this is a brief overlay of the wonderful team we have in the Qubit lab in UCLA. I deeply appreciate everything they've done and their presence. Thank you.
Thank you. Thank you very much. So I got a little confused. Is Aisha going to say something too, or no?
Oh, I think she'll just be
around,
corralling some of the questions, perhaps if there's some sort of mistranslation going on. I think when I was discussing when we are discussing CISS, at least in our lab, there is a lot of confusion because everyone comes from different fields too. So
okay, very well. So let me then ask: are there any questions? Yes, Peng.
Yes. Can you hear me?
Yes, I can.
Oh, okay. Thank you. It's a very interesting talk, and so I have a comment and a question. Yes. So the comment was and I applaud you for pointing out the importance of the the spin interface and the role of substrate. So because of that, I would caution against that presents a lot of difficulty in extracting spin polarization from, say, the spin valve measurement. So I would really caution against just using some simplistic definition of spin polarization, for example, from the difference in the two currents in different directions. So that's my comment. And my question is, do you have any sense on the relative importance of Elliott-Jaffet versus Diakonoff-Perot relaxation mechanisms in CISS, especially in chiral molecules? So in semiconductors, the EY is more important on the insulating side, and the DP is more important on the metallic side. So do you expect, some? I assume the transport in the organic molecules would probably be tunneling or hopping. So does that imply EY would be more dominant, and is there a way one could tune this in experiments?
I think this is a very interesting question, because I think when we think about our EY or DP pictures, we seem to assume we can have some sort of very concrete picture of what exactly happens to our spin currents, which is of course not the case given our what we have in experiment. Personally, I do think that the DP picture should hold more weight. I assume that the DP picture should hold more weight. Of course, one by virtue of the fact that if you switch your tip magnetization directions, you get a very different sort of decrease in current flow depending on how long your molecule is. But at the same time, I can't really say with any certainty what we might expect just from this alone, because ultimately it does feel like very much like a black box. I'm not sure whether the band gap between your up and down states at the Fermi surface is large enough to completely invalidate the EY picture or not. And I think that is one of personally my biggest confusions when I'm looking through the literature, and why I think it is very important to have some sort of first principles analysis. So
yeah, I'm just not sure, do we have any concrete examples of definitively diffusive transport through especially long molecules, right?
No, we don't. Anyways, but here at the lab, we are trying to design experiments and procure the machinery available to probe such timescale properties. But as of yet, we do not have this capability. We do not have this insight.
Right. Thank you.
Yeah, thank you. Hope I've answered the question.
Thank you. Sebastian has a question, or maybe more.
Yes, it's more. Thank you, Jonas, and thank you, Yanchi Fu, for the great and big talk. I have more than one question. Could you maybe go back to questions to the end?
Okay, yes.
Yeah, precisely. So what exactly do you mean with how much does CISS owe to the temperature versus geometry? Do you so should I maybe you answer and then it will become clear what exactly you mean by that?
Okay, I think this stems from what we mean when we're talking about chirality, because for example, from a chemistry point of view, you have a chiral molecule when you simply have a chiral center, like let's imagine some sort of tetrahedral molecule, and you've got your central atom that is bonded to 4 different groups. This alone breaks all your mirror symmetries and gives rise to chirality. So then we have of course, the issue of temperature is very important, as we all know, but the issue of geometry is a more subtle point. Suppose I have a linear chain, some sort of beta pleated sheet that has no twisting whatsoever, and suppose I just add one chiral group, one chiral center onto it. How will this impact CISS? How much CISS do we owe to the secondary structure, the structure of electron transport within space versus the chemical properties of the molecules we are investigating?
Okay.
So this is kind of what I have in mind when I'm thinking about temperature versus geometry.
Okay, yeah, that is good to know. I was thinking about something similar because one can perform these two terminal setups where one measures the different currents corresponding to the different polarizations or the different helicities. One can make this with all kinds of helix structured molecules. Now, and then one could, I was thinking, you mean one could measure the spin polarization as a function of curvature of the helix and temperature, no? And and here are some comments regarding this. So Jonas wrote a paper about how the temperature dependence of these two terminal setups is influenced, and he reproduced some experimental data in he reproduced some graphs. So if you write me an email, I can send it to you. Ron likes that paper a lot. And also with this quantum transport, there's actually lots of literature which always uses the Landauer-Bütikow formula. I'm not sure whether you know about that. No?
Ah, yes.
And yeah, and then I have two more questions. Namely, I didn't entirely understand when you were talking earlier about the construction recipe of a model for CISS. You started with a Dirac equation, no? And yeah, I mean it is good. Back to the roots, no? I appreciate that, but I didn't entirely understand what you were what you meant with non-inertial effects. What non-inertial effects are you referring to? I mean, why should the Dirac equation change due to which effects?
Okay. Hold on, let me gather my thoughts on how to phrase this.
Yeah, please take your time. No?
Okay, right. So the gist of it is that our Dirac equation, by pure construction, only describes a Dirac fermion whose frame has been boosted in the z-axis. So we can imagine that our Dirac equation only describes an electron that is basically undergoing some sort of constant velocity, motion in constant velocity, some sort of non-appreciably accelerating motion. And this is an approximation that we can generally get away with in everyday life, because the ultra-relativistic corrections that we would then have to consider are usually quite minor, and there's really no need to consider these. Normally, the context where we see this generally covariant Dirac equation actually arises in general relativity, where we have to consider how a fermion moves in curved space-time. And of course, this is not curved space-time. I think there are some papers, CISS theory papers out there that do try to argue along, or that do kind of misuse this terminology, and they say that, okay, we use the Dirac equation for curved space-time, when in fact, you are in flat space-time. You're simply embedded on some sort of submanifold. And in order to properly extract the motion of your Dirac equation, of your Dirac fermion along this kind of curved path, a curved path that, as we can imagine, for example, when we have a ball or some sort of planetary orbit going around in some sort of circular motion, that is not inertial motion. There's some sort of Coriolis force. There are some sort of centrifugal forces out there that dictate very strongly the dynamics, the kinematics of its motion. And similarly, right here, we try to incorporate these very same geometric factors right from the offset, because otherwise they would get completely lost.
Okay, but aren't they included in the consideration by switching to this Frenet-Serret frame?
No, this is just the Frenet-Serret frame is simply like a map. It is simply a way by which you can define coordinates and define some sort of system by which you follow your motion. The equation is the Dirac equation is an equation of motion. When we try to use the Frenet-Serret frame with the normal Dirac equation, this in itself is actually a bit of a contradiction because they do not sit very tightly with each other. So normally, I think in some papers, I can't exactly remember which authors they were by, but what they normally do is they kind of take a bit of a shortcut. Well, it sounds a bit bad, but honestly, the whole endeavor is very, very tedious. So this is something that I can really sympathize with, where they take the Da Costa thin layer quantization and they skip the Dirac equation. They just start immediately from, okay, we have our unrelativistic Hamiltonian, we're going to add a spin orbit coupling, and we are going to add some sort of correction based on our Da Costa thin layer quantization within our non-relativistic Hamiltonian, and the rest is not accounted for. So this is a general approach that I think some have taken, but that of course doesn't exactly illuminate as much as we would have hoped it to illuminate.
Thank you. Do you mind? It's an interesting discussion, but I think it's diverted a little bit from the scope. So there are the comments. I noticed Ron has a comment on some things you mentioned earlier.
I want to remind you that there are more and more evidences that the spin polarization in the CISS effect, measured by different methods, not only by switching the magnet and so on, correlates with the optical activity of the molecule. That's a hint that the single electron picture is probably not sufficient to explain the CISS effect. And so what do you have to say about this?
Honestly, I think you're right. And of course, this is why I have to reiterate once more that this consideration of first principles doesn't just come from a CISS-centric perspective, but also a general quantum spintronics perspective when we are trying to design some sort of qubit manipulating device. At least personally on my end, I am personally not very clear about how photoexcitation processes and electron transport can give rise to some can directly whittle down.
Sorry, one has to be careful here.
Oh, yes.
When you speak about CD, of course, we measure CD by photo excitation, But what it really means that the electrical polarizability and the anisotropic electric polarizability play a role. So it's polarizability effect, which of course involves excited states, but you see it also in the ground state. So it's not really photoexcitation.
Okay, yes, I
So that's
see your
important.
point now. Yes,
And
yes.
it really, and you can easily visualize it if you think about electron going through a system, nanometric system, where there are other electrons, and of course the other electron responds to the charge of this electron. We know that if you add an electron to a molecule, the electronic structure of the molecule changes.
Mhm.
So that's not surprising.
Thank you for the comment. I did not consider that.
Yeah, and may I sort of add on? I think what Ron says is very important, and I think we from the physics community have a tendency to forget about exactly this, because when we think about metals and semiconductors, well, if you add an electron, it changes, but it's probably negligible, so we don't care. But for a molecule, it makes a huge difference. I mean, if you have so many few elements in it, and you add an electron, that's a massive change of whatever happens there. And I think us physicists, we have to acknowledge that fact and somehow take that into account. It's not easy, but it's still our job to do it, right? So no, but seriously, I think it's really important that having one electron extra or one electron less, it makes a major difference, because it can change a lot of things in the structure. Yeah. Are there any more questions? Maybe Sebastian has another, but I interrupted you. But
Yes, I wanted to wait for the end now. If there is no other question, then I would have another one. Namely, I have seen it now numerous times, and I very successfully misunderstood it every time. But could you maybe explain the correlation between the spin polarization and the charge polarization that you mentioned on one of your earlier slides?
Okay, hold on, let me.
It was one of the experimental phenomena that you presented in the context of CISS, precisely down there. Yeah,
there's the spin blockade mechanism, right? I think since Ronaman is in the call, he might be able to correct me if I have misunderstood something. But what I see it as is basically there is on one hand, of course, when you have your current flowing through your molecular junction, you get some sort of induced dipole within your induced charge dipole within your molecule. The question of how this correlates to spin polarization within the molecule is more involved. Let me try to write it out. Let's just go back to okay, never mind. Can I draw? Okay. So, oh dear, draw. Okay, I can't let go of the button. Okay, so let's suppose we study the Fermi surface of a material. So we have, for example, here some Ky.
But in a way, I'm not sure one has to make it complicated. I think an easy picture to see that they should be correlated is that when you charge polarize, well, don't you have motion of electrons inside the molecule?
All right. Yes.
I mean,
it's
a reorganization of your charge. So once it's charge neutral, and then when it becomes charge polarized, well, the charge has moved somewhere and this motion is accompanied with the spin polarization in the sense that it is when we drive a current through it. Maybe it's too simplified description, but I think the intuition could perhaps be enough for that. I'm not sure. What do you say, Ron?
Basically, that's the right intuition. Yeah, it's a charge reorganization is accompanied with spin polarization, and we have experimental evidence for it. And we see actually that when we apply different field on the molecule, the charge reorganization and the spin polarization scales with the speed with the applied field. So that's observed, and therefore I don't think it's such a miracle. It's not surprising at all. Actually, it's consistent with everything we learned from the CISS effect.
Yeah.
But
I would just add to that we also see the inverse, right? When we apply a magnetic field, we induce charge polarization in chiral molecules.
Right. So they are kind of reciprocal in that sense.
Yes.
okay. Yeah, thank you. That was no, I want to add again, yeah. So in this two-terminal setup, yeah, and I drive a current through the helix, yeah, and then I see a spin polarized current. I see a different current versus voltage curve for different magnetizations. That has something to do with charge polarization, or am I now confusing things?
No, yeah.
It's not the place to start now, go through all the theories. Actually, there are papers, both by Jonas and I think now Per is coming with a new work,
okay.
and in which they explain it in a very explicit way. So
Okay, sorry. Yeah, that's I didn't know that I opened a whole bottle of things that one has to explain there. No, then let me do.
Could I add a quick point?
Peng. Yes, Peng.
Yeah. So I think there's an interesting point raised by Binghai Yan. In one of his models, the charge polarization could actually modulate the tunnel barrier, and that changes the conductance through the this two-terminal device, and that could change by a lot. And so again, this change of conductance or the change of current in opposite directions may not be directly reflecting the spin polarization, but a modulation of the tunneling current, which could be huge, even with a small modulation. Yeah.
All right. It's getting late. Maybe it's about, well, and half the audience have left, so maybe it's a sign that we should try to wrap it up. I would like to thank you everybody for coming here and listening to Yanxi talk, and thank you very much, Yanxi, for giving your presentation, and for the next time, then, according to tradition, first of all, I will try to be better on the announcement that time, hopefully. On my schedule, I have, that's for November the 23rd. It's Wei Qin from Shandong University. I hope it's going to be that. If not, it's going to be something else. So let's meet here in 2 weeks again, and I wish you a pleasant time until then. Bye-bye.
Hello.
Goodbye.